Moving on with Unit 13, the I CAN statement for 13.2 is I can analyze and interpret data sets. So we'll write data right here. Data sets, displays, and statistics. So the focus of what we're going to do today is about analyzing and interpreting those data sets and their displays and statistics. So a reminder here in the warm-up, it says statistics is the science of using data to make decisions. So let's write the word decisions right here. We also talked about the fact that it can be used to make some good arguments. So we can convince people that we're right, that we're making the right decision, or whatever it happens to be if we know statistics really well. Now, statistics really become useful when we know how to apply them in real-world situations. And that's going to kind of be the focus of today. And we can also avoid being fooled, so we'll write the word fooled right here, fooled by statistics if we know when each type of statistic should be used and what to look for when data is displayed, because even displays can be a little bit deceiving sometimes. So analyzing data makes us think in a very critical way, and that's a really good skill to have. In fact, that's one of the great things about statistics is we learn a little bit about it, and then we're better consumers of information because we understand what to look for, when to be suspicious, and things like that. So here's example 1. It says, in an interview for a job, the owner of a company tells you they have 17 employees and their average salary is $50,000. The owner gives you a handout with the information below and you examine it carefully. So this is that interpreting and analyzing that we're talking about. So let's take a look at this and let's think about this. So these are salaries in thousands. We've got a histogram right here. So this would represent ones in the 20,000s, 30,000s, 40,000s, and so forth. So you look at that and you go, well, wait a minute, 50,000 is about right here. We kind of look at this display and then we say, wait a minute, look at this one way up here. So then we look at the numbers. So he gives us the actual numbers. These are the salaries in thousands. And it starts off at 29. He did do the favor of putting these in order. So whoever the boss is said, hey, we start at 29 and go up to 110. So that's great. We've got the 5-number summary here, along with those descriptive statistics of mean, median, and mode. And when he says 50,000, there's that 50,000 right there. And then we look at this display. So here's a box plot, and we can see that it starts off, the minimum's 29,000, the maximum's 110,000, and then we see that median right there of 42. Now, do you notice anything about how things are spread out in these displays? And do you notice anything about the numbers up here and these descriptive statistics in this middle box right there? Well, what you might want to notice about these is most of them are in the 30s and 40s. So most are around, so we'll just write most are around 30 to 40,000. They're somewhere in that range. There's a whole bunch of them, a whole bunch in the 30s and a whole bunch of 40s. Those are our largest groups. And then the next question is, well, is the owner telling the truth? Well, the technical answer to that is yes, he is, because of this 50,000 median right there. And because the owner is technically telling the truth, but we see a little bit of discrepancy here, it might lead us to think a little bit more critically. So, what statistic would be more accurate than the mean in describing the average employee's salary? Well, if we know that it looks like most of these scores are in the 30s and 40s, somewhere around here, it might be that the median is a little bit better. So let's say the median right here, oops, a little bit of space right there. And if somebody asked us to say why we think the median is better, we could say something like this: it's just more typical. It's a little bit more typical of the average, in air quotes there, of what the average employee makes. So I'm going to slide down here and let's talk about this display. Now, nearly anybody who looks at this data and sees how this is displayed, they would know that there's something a little bit unusual about this. And what most anybody looking at this would notice is this is kind of a funny shape right here for both the histogram and for the box plot. And there's one data point that is much, much bigger than all of the others. This 110, it's much, much bigger. Okay, so we'll write bigger right there. Now, when displays have a long tail on one side, they are said to be skewed. So we'll write the word skewed right here. Let me make that look right. Okay, S-K-E-W-E-D. So here's some common distributions. So let's talk about these guys here. So this first one is a pretty common one. This one is said to be symmetric and bell shape. So symmetric means there are two halves that look the same. So if I were to draw a line right here down the middle, the left half looks like the right half and so forth. This one here, the same thing is true. It's symmetric, so let's write the word symmetric. It's symmetric, and a different word than bell shape. That's kind of shaped like a bell. This is called symmetric and uniform. And this one is skewed, and the way we say it's skewed is we say the direction of the skewedness is by the tail. So we would say that this is left skewed because the tail's on the left, and by the same token, this one over here, this would be right skewed because the tail is on the right. And what skewed means is it's distorted toward one side or the other side. So here it's skewed to the left, and here it's skewed to the right. Again, we name the skewedness according to where the tail is. Now, when a point is detached from the main cluster of a data set by a significant amount, so there's a big spread in between where most of the data is and then where one particular point is, then we have a name for that. We call that an outlier. Okay, outlier. So we'll call that an outlier, and it kind of looks like on this one that this one might be an outlier. This 110, it's way away from that other set, and you can see how stretched out that top quarter of data was when we did the box plot up there. Okay, so we're going to go back to example number 1, and we're going to name the shape of the histogram, we're going to label the outlier, and we're going to mark the location of the mean and the median. So I'm going to come up here and we'll look at this and we'll give this a name. So because this kind of has a tail to the right, we're going to say that this is right skewed. And you can either say right skewed or you can say skewed to the right. So that takes care of the shape. And you can also kind of see that there might be a long tail here in the box plot as well. And then this right here, we're going to call that an outlier for the time being, because that's really far away from the other ones. And then we're going to do something else, and this is really important that you catch this. We're going to mark where the mean is and where the median is. So the mean is at 50. So I'm going to put a mark right here, and we're going to say the mean is at 50. So I'm going to say mean right here. And the median is at 42. So 42 would be about right there. Okay? So somewhere about right there. And this is the median. So this is the middle score, but this is the arithmetic average. Okay? So keep that in mind as we move forward. And let's come down here on example 2, and let's take a look at these two here. So it says, what do you notice about the data in sets A and B below? So here's the data set A, here's the data set B. And it says we've got their displays, their means, their medians. So what do we notice about this? So on this one, we've got a mean of 8.5 and a median of 8.5. So I could put this line right here like we did before. I could draw where that is. And this is the mean and the median. So not only is it the arithmetic average, it's also the middle score. So you'll notice that this is symmetric, not quite uniform and maybe not quite bell-shaped, but that looks pretty good there. Okay, and then let's take a look at this one over here. This is shaped almost identical to that, but basically what's happened is we've taken that little rectangle that was right here and we've slid it way over there, and notice what's happened. The mean is 7.5, but the median is still 8.5. So the median, 8.5, I'm going to draw a line right here. This is the median, and the mean is at 7.9. So 7.9 would be about, we'll call it about right there, okay? So right there, that is the mean, all right? So it says we've marked the locations of the mean and the median on the histogram using those vertical lines. And here's what we want to notice. When data is roughly symmetric, the mean and the median are about the same. They're nearly always, really close to identical. And we need to say roughly symmetric because very seldom do things happen like this. Like this is perfectly symmetric. We've got two of these rectangles on either side and then two of these larger rectangles on either side. All right. So when data is skewed, the mean tends to get pulled in the direction of the tail. So if it's not skewed, the mean and the median, they're really close to one another. And when it is skewed, notice that this is skewed to the left. So this is left skewed. The mean gets pulled to the left, meaning it's smaller than the mean, okay? Now, in general, if the data is roughly symmetric, the best measure of center is the mean. And if the data is skewed, the best measure of center is the median. So this brings to mind what we were talking about up above. So I'm going to slide up here and we're going to take a quick look at this. This explains why we were a little bit suspicious of this data that the owner of the company gave us. The data is skewed, and when we had this big outlier, somebody was making $110,000, what that did is it took the mean and it drug it this way, drug it to the right, made it larger. So that's why we have a mean of 50, but a median of 42. And remember, we said, hey, if most of the scores were in the 30s and 40s, we ought to be saying that the typical employee makes somewhere in there, and that's why the median was probably better there. So let's go ahead and take a look at the other side. So to kind of summarize that job interview data, the moral of that story is if the data is skewed or it has outliers, so really extreme data points, then we should be really careful with the data and deciding what statistics are best to use to describe that data, and we want to be able to interpret it as accurately as possible. Now, outliers and skewedness, that's how we'd say that, have very little impact on the median. All right, so if we've got a large data point, if we've got an outlier, if it's skewed and things like that, it has very little impact on the median. However, the mean, so write the word mean right here, it is really sensitive to skewedness and outliers. So we should be really careful whenever the mean is used, and that's what we were talking about right here. If it's roughly symmetric, go ahead and use the mean, but if it's skewed, and perhaps if it has outliers, then we probably ought to be using the median. Now, on example 3, it says answer the questions based on what you know about the distributions and statistics. So here's what it looks like. And it says, how would you describe the shape of the distribution at left? So this one right here. So the tail goes off to the right side. So we would say that this is skewed right. And then it says, how would you complete the sentence using a greater than, less than, or approximately equal to? So remember, if this is skewed to the right, that means the mean is going to be bigger than the median. So if we put the median, say right here, say that's the halfway point, and I'm going to just write median right here. The mean gets drug in the direction of the tail, so maybe the mean is about right here. So the mean would be larger than the median because it's right skewed. And then it says mark the appropriate location of the mean and the median. Gosh, we kind of have that done already. And it says which is the best measure of center, mean or median, and why? Well, we would say median, and the reason for that is because it's skewed. Whenever we're using a skewed data set, the best measure of center is probably the median. And again, there's some variation on that, and it depends on how skewed it is and stuff like that, but that's a good general rule. Now, taking a look at example 4, it says answer the questions based on what you know about distributions and statistics. So this doesn't have anything to do with up above here, so let's take a look at this. It says, what can you say about any data set? So any data set and its distribution if you knew that the mean is 19 and the median is 25. So I'm going to put the median right here of 25 and the mean right here of 19. Well, they're not close to each other, so what that means is this has probably been skewed. Now remember, the mean gets drug in the direction of the tail, so the tail would be on the left here, so this would be left skewed. Okay. How much it's skewed, we don't know without the rest of the data, but that's a pretty good thing right there. And it says, what could you say about any data set and its distribution if you knew the mean is 10.2 and the median is 10.1? Well, if we located the two of those, 10.2 might be right here and 10.1 is right there. They're really close to each other. So what we'd say here is we would say that it's roughly symmetric. Roughly symmetric. Okay, let's slide down here and take a look at these others. So distributions that are symmetric and bell-shaped, so both of these, they come up quite often when we're studying data, especially when the data is gathered from real-world situations. Now, because they come up so often, we have a name for this distribution. So they are called normal distributions. So write the word normal right here. And here's an example that you might remember from 7th grade. So we did some probability in 7th grade, and we may have done an experiment, or you may have done an experiment like this. So students tossed coins 16 times, and what they recorded was how many times their coin landed on heads. So they just kept track of the number of heads. So they could get 0 heads all the way up to 16 heads. And here's what it looks like, okay? So what is the shape of the distribution? Well, the shape of this is symmetric, so I'm going to abbreviate this way. Symmetric and bell-shaped. Symmetric and bell-shaped. We can give a special name to this. This is called a normal distribution. Okay, a normal distribution. It says approximately what is the mean? Well, because this is symmetric, we know the mean is going to be roughly right in the middle with the median, so we would say it's about 8. So I'm going to draw a line right there. All right, so it's going to be about 8. And again, because it's symmetric, that's going to be about the middle. The median is also going to be 8. And then what they want us to do is they want us to draw a curve along the tops of each one of the rectangles, and this is called a normal curve. So what we're going to do here is there's no rectangle here, so we're going to kind of start here, and we basically want to hit each one of these kind of like that. It's going to come up here, and then it's going to go down like this. So if you ever see something that looks like this, and then with this curve on here, you can kind of get a sense as to why they call this a bell shape, because it kind of has the shape of a bell. That's what it looks like, and this is called a normal curve, and that normal distribution, all of those histograms that make that normal distribution, they're kind of underneath there, okay? And it says, why are the mean and the median roughly the same? Well, that's because it's symmetric, so let's just write symmetric right here. Because it's symmetric, and it says what would happen to the mean if several students reported getting 16 heads. So if there were 16 heads, so there were a bunch of students, we had the class data, and then there were a couple that came in and said, hey, there were 16 heads and when I flipped these coins and stuff like that. So if we had a bunch of them, it turned out to be this. So if we had something like that, what would we say? All right. Well, what would happen to the mean is, because this would slowly have a tail that's a little bit bigger, it wouldn't be as symmetric anymore, it would get drug in the direction of that. So what would happen to the mean? The mean would increase. Increase, which means, of course, it's going to get bigger, okay? The mean would get bigger. It would get drug in the direction of that tail, of that outlier there. Now, do you think 16 heads would count as an outlier? If you flip a coin 16 times, would it be very likely that you get 16 heads? Wouldn't happen very likely. It might be an outlier, and the rules for outliers are really complicated. So for right now, we're just going to kind of look at things and say, yeah, that kind of looks like an outlier, and we're going to learn some rules for outliers in the next couple of lessons. All right, good luck with the assignment.